Hello everyone, I'm Fanzo and I'm a graduate student working with Niel at Penn State. And in this talk, I'm going to talk about the Dwarf AGNs and how do we search for them in the SST deep drilling fields with X-rays. Okay, so active dwarf galaxies are just dwarf galaxies containing AGNs, and dwarf galaxies are defined as those with stellar mass below the threshold. And I think they are a very important population because first they may play important roles for dwarf galaxy population. But for AGN stuff, we may care more about the black holes residing in them. And these dwarf galaxies can contain intermediate mass black holes. And these intermediate mass black holes can be the remnant of seed supermassive black holes at high redshift. And they may be the primary targets of next generation gravitational wave detector, LISA. And I think for LSST specifically, it's becoming increasingly interesting because LSST is going deep enough to probe the dwarf regime in the wide survey. And this is not allowed in previous surveys. And but how do we search for intermediate mass black holes or active dwarf galaxies, especially beyond the local universe? So just like for AGNs or supermassive black holes, the most reliable way is to use a dynamic search, but this is quite limited to very nearby galaxies. And people have mostly been using the optical spectrum, especially from SDSS or gamma, to select such type of sources. And this method is again limited to the local universe and proven to be inefficient. And for AGNs, people have been thinking of the medium fresh selection, but unfortunately, this method just simply doesn't work for active dwarf galaxies. And so essentially, we have three methods left. We have radio, X-ray, variability, and I want to emphasize the overall selection is still in its infancy stage. And I probably have spent like 3 days working on radio selection in deep drilling fields, but I simply failed. Probably more careful work can return better results, but currently I am only convinced that the X-ray and variability will work in, especially in the deep drilling fields. So, and this work will present the X-ray results, and the LSST will give the variability selection in the future. So, as Niel mentioned yesterday, we are focusing on the deep drilling fields, and I'm only looking at the three LSS deep drilling fields: XMM LSS, WCFS, and ELSS1, which is covered by XMM surveys. And this is currently the largest medium depth X-ray survey, allowing us to select the largest sample of active dwarf galaxies beyond the local universe using X-rays. And in comparison, Cosmos also has extensive data, and the active dwarf galaxy has already been selected there in Cosmos, and we are just enlarging the sample using the new X-ray coverage in the other three LSS deep drilling fields. And the active dwarf galaxy, prior to the active dwarf galaxy work, we have also done lots of multi-wavelength preparations. So in the paper last year, we have compiled the multi-wavelength data in these deep drilling fields, and also analyzed the spectral energy distributions in a systematic way. We have classified sources into like stars, AGN candidates, bursting or quenching galaxies, and normal galaxies, and fitted them very carefully. And the figure in the bottom right panel shows some LCD fitting examples. And we also discussed LCD-based AGN selection and calibrate them. And I think more importantly, we catalog the host galaxy properties and compare, as you can see, we also calibrate them with other previous results. And with the X-ray survey I mentioned, and also the multi-wavelength, the host galaxy catalog, we can now move on to the selection of active dwarf galaxies. And initial idea is simple. We just select actually detected sources. And if their stellar mass is below this threshold, then we call them as active dwarf galaxies or at least candidates. But things are much more complicated than we previously thought. And we have faced lots of problems. And I think this is the biggest one, the photometric ratios. And we found that the photometric ratios of dwarf AGNs are highly unreliable because of the young stellar age and the AGN contamination. I'm showing the QZ versus specific sublimation rate and also the AGN fractional AGN contribution to the whole SCD. And QZ here is just an empirical parameter for quantifying the photo Z reliability. And larger QZ means that the photo Zs are more likely to be problematic. And here I'm only showing the X-ray sources with spectroscopic redshifts, and I color code them using the difference between the spectroscopic redshift and the photometric redshift. And so look at the left-hand figure. You can see that as specific stuff measurement increases, the color is getting darker, and the darkest brown points are just catastrophic outliers for photo Zs, and they are just useless. And in the meantime, the QZ also increases with specific transformation rate. And in the right hand figure, we see the same trend. As AGN fraction goes high, the photo Z gets much worse. And these big points are our active dwarf galaxy candidates, and you can see lots of them are actually catastrophic outliers in terms of their photo Zs. So this causes lots of problems, and we just use the empirical criteria to select reliable photo Zs. We think that if the QZ is below 0.15, as shown by the black curve here, and then we think the QZ may the photo Zs may be more reliable, and we apply this criterion back to the sources without spec Zs. So here is the result. I'm plotting the specific transformation rate versus AGN fraction, and the sign points are those with spec Zs, and they are scattered across the plane. And no matter what the photo Zs are, we always keep these spec Zs. And but for those only with photo Zs, we just remove them if their QZ is large. So we remove these red points. So you can see that these criteria have exerted very strong selection effects to our sample. And this is for the photo Z only. And then we also care about the stellar mass. And here is an example that whose stellar mass is just unreliable. Is SCD, you can see it's totally dominated by the AGN emission, and we cannot really reliably measure the galaxy component. So to avoid such cases, we use another criterion. So first, our stellar mass is measured based on feeding the SCD with an AGN component. And then we remove the AGN component, we only feed it with a galaxy component. So that means we attribute the AGN emission to its galaxy emission. So you can think that this galaxy-based stellar mass will be roughly a soft upper limit for its actual stellar mass. And we plot the galaxy-based stellar mass versus AGN template-based stellar mass in this figure. Also, I color-coded them with the redshifts, and you can see for high redshifts, we have lots of sources with galaxy template-based stellar mass much larger than the AGN template-based stellar mass. And such sources are just like this one. It's totally dominated by the AGN emission in terms of its SCD. And we thus remove sources whose galaxy template-based stellar mass is also above this stellar mass threshold. And this remove lots of high redshift sources. And then we also remove sources with without strong X-rays. I mean, if their X-ray signals cannot be justified to be from the AGN, then we remove them. And here I'm showing two examples. In the top panel, this source is blended. We have two AGNs together nearby, and we are not sure which one is really the fraction of these X-ray signals from the dwarf galaxies. And in the bottom panel, the X-ray signal is just too faint, and we are not sure whether the X-ray signal is from the galaxy X-ray binaries or from the AGN emission. So with this criterion, we now have 73 active dwarf galaxies, and here I'm plotting the X-ray luminosity versus redshift, and the background gray points are general X-ray sources, and these red points are those sources removed from our candidates, and the blue points are our final sample. And I think this figure clearly shows you how challenging it is to select active dwarf galaxies, especially if you want to go to the high redshift. And all the sources above V of 1 are simply removed. And even down to low redshift, we also have a limited fraction a limited successful rate of selecting such active dwarf galaxies. Given these strong selection effects, so it's challenging, but we want to do what we can do. We have this sample, and we can still do some basic population analysis to this source. So we check various things. So first we check the X-ray property. We check the hardness ratio, which is defined as the hard band minus soft band over hard band plus soft band count rate in the X-ray. So higher hardness ratio just means higher obscuration. And I'm plotting hardness ratio versus redshift for 3 fields here. And these colored points are our active dwarf galaxies, our confirmed active dwarf galaxies. And I also plot some expected curve for observed power law with different obscuration level. And so you can see that we don't really have lots of sources above the 10 to 23 NH curve. But if we use X-ray luminosity to predict that, I mean, the X-ray luminosity function with NH distribution included, then we will get about like 15 sources predicted from the X-ray luminosity function. But this is not observed, and so this just implies that X-ray luminosity function is not valid anymore for active dwarf galaxies. Probably because active dwarf galaxies have lower black hole mass, and at given luminosity, their adenine ratios are higher, and we know there is an anti-correlation between adenine ratio and the obscuration. So that probably can explain why there are less heavily obscured sources seen in our active dwarf galaxy sample. So that's the first result, and we also check the environment of active dwarf galaxies. We use the projective separation between our dwarf target and the nearby massive galaxies as a trace of the environment, and we found that once we match on the stellar mass and the redshift, then we wouldn't see any difference between active dwarf galaxies and the inactive normal dwarf galaxies. Okay, and this probably means the environment is not directly responsible for the AGN triggering mechanism for dwarf galaxies. And so then I will talk about some problems. So we try to look at the adenine ratios, but although we know that it's challenging, here is what we do. We know it's stellar mass, then we just scale it down to the black hole mass. Means a very crude estimation. And we also have AGN volumetric luminosity from the LST feeding. And then based on this, we can define, we can estimate the Eddington ratio. And in the left-hand figure, I'm plotting the AGN volumetric luminosity versus black hole mass. And I also plot some constant Eddington ratio curve. And you can see our sources generally have very high Eddington ratio based on this estimation. But we think that there must be something wrong. And one direct evidence is shown in the right-hand figure. I'm plotting the again volumetric correction versus Eddington ratio, and the correction is defined as the volumetric luminosity divided by actual luminosity. And we have some observationally calibrated relation between these two quantities, as shown as the black curve. But our sample, as you can see, is significantly located below the expected relation. So that means something must be wrong, and actually there are lots of things could be wrong, and I will discuss that. So I think the most one of the most fundamental issue is about the black hole mass. As black hole mass scales down, the accretion disk temperature increases, and I'm just using a standard thin disk model, and I know there are more a much better disk model, but here I'm just using this as an illustration purpose. And as the black hole mass scales down, the disk LCD shifts toward higher energy. But for our LCD feeding, we are using a fixed temperature disk model. Is calibrated from quasars, and quasars have much more massive black holes than our sample. And this means that we actually neglect the peak of the disk emission. So this probably will cause underestimation of our AGN volumetric luminosity, because to get that, we need to actually rely on a model to extrapolate from our observed data to the whole disk LCD. But this should be done very carefully. And in our model, we didn't account for that. And I think someday we should put this AGN, this temperature dependent AGN model into the LCD feeding code. But I don't think there is any ongoing effort in doing that. I mean combining AGNs and Galactic together with an temperature dependent AGN model. Okay. And also we know that the black hole mass and the stellar mass relation have very large scatters, and we know, so this probably will cause some Eddington-like bias. And also we know that X-ray over UV ratio becomes larger with decreases black hole mass, and that, so the third point means that the relation itself actually probably will go down a little bit for actually dwarf galaxy. So my point is that there are lots of uncertain things going on, and any of them can cause lots of troubles, and I'm not sure which one is actually the cause. And but I think this leaves lots of opportunities for further improvement. Okay, and our last result, and I think this is probably another one of the most important results of this work. We have measured the accretion distribution, and this is so accretion distribution is defined as the probability density in the log space of a source with given stellar mass, given redshift, hosting an AGN of Lx, and we assume a power law to fit that, and then we apply this model to our data to constrain these parameters, and we can then integrate the accretion distribution to get the so-called AGN fraction among the dwarf population. And we have two ways to define AGN fraction. One is using the luminosity-based AGN fraction. We define AGN we call the source an AGN if it's actually mostly above a threshold, or we have a specific accretion rate based AGN fraction. So it uses the lambda as DHAR, which is just defined as the actual velocity divided by stellar mass times some constant to mimic the Eddington ratio. And we found that the luminosity-based AGN fraction increases with stellar mass, but the specific accretion rate-based AGN fraction generally doesn't. It more or less follows the flat trend between the dwarf galaxies and also the massive galaxies. And we also checked the redshift evolution. So in the right figure, compare our AGN active fraction with previous work. So and there are lots of uncertainties, but overall they are consistent. And from this figure, we cannot see any clear redshift evolution. But that's probably because our sample size is not sufficient. I suspect we need at least 6 times larger sample to actually confirm the redshift evolution if it really has a redshift evolution. Okay, and so that's for the general population. And I also found an interesting case as a condensate dwarf AGN candidate at high redshift. So as far as we know, there is no confirmed condensate dwarf AGNs beyond the local universe. So I think this source is quite interesting. And so we found this source because it has high harmonics ratio. As you can see, it is circled in the XMM LSS figure. And we then analyze the XMM and also Chandra spectrum, and we confirmed that its color density is pretty high. It's 10 to 24 with the soft gamma, although the gamma is mainly constrained by the soft excess. And it also has, a crazy optical spectrum. It has lots of high ionization lines, such as helium-2, neon-5, etc. And neon-5 requires almost 100 EV for its ionization. And we also found, like, for example, its H beta is broad, but if we look at it more carefully, it's actually broadened by the outflows. The H beta profile is exactly the same with the oxygen-3 profile. So I think so overall it's a narrow line AGN and with some outflow. And but the problem is that the reason I call it a candidate is not because of its condensate signature, but its stellar mass. We found it's very hard to constrain stellar mass because it's starburst AGN. And if it's only an AGN, we can still do a very good job in constraining stellar mass. But the problem is that it's a starburst galaxy plus an AGN. And this causes lots of trouble. I'm showing 2 kinds of acidic feeding. One is from this work, one is from the previous acidic work, and the middle panel is the revised acidic feeding in this work. And we have 2 kinds of good acidic feeding results, but they have totally different star formation history, as you can see in the right panel. So the problem is that in the near-infrared band, we don't know how much is contributed by the AGN or contributed by the galaxy, and this leaves a lot of room for the existence of old stars, and so it's probably that this source also could have a much larger stellar mass. Like in the extreme case, it's 4 times 10 to 10 the stellar mass, solar mass. So obviously, this won't be an dwarf galaxy if that's true, but we are not sure which one is the case. But I think that with like high resolution infrared imaging and in the H or KS band, we can solve this issue. Okay. So I will go to the summary. So overall, we have selected 73 active dwarf galaxies. And this is currently the largest sample beyond the local universe selected in the X-ray. And we know that there are lots of selection biases, but we are still able to calculate the basic properties such as obscuration, host environment, addition ratio, and activation distribution. And also we check the radial property, which is not shown here. And we have identified several practical issues, and I think these issues are also important for future dwarf galaxy work. And I think the most important lesson I've learned from this work is that general tools for massive galaxy or massive AGN simply do not necessarily work well for active dwarf galaxies. We need much more careful work to understand what's going on with the parameters returned from such kind of software or packages. And I also want to emphasize that this sample will have, so LSST will have variability-based selection in exactly the same field. So we will have X-ray. We now have X-ray selected sample, and we are waiting for variability selected sample from LSST. And that's all. I'm happy to take any questions.
Yeah, there are so many exciting results, and I guess I need to pick up the one that I'm most interested in. So you mentioned that the SCD fitting can give you the host galaxy properties, and I wonder if there's any efforts, or have you think about using like image analysis, say some traditional image decomposition, to get, let's say, the optical flux of the host galaxy, and how does that compare with your SCD fitting results? I mean, this is kind of related to the last, competence SIG AGN you mentioned.
Yeah.
Because you said there's kind of many uncertainties in the near infrared flux of the host galaxy. I mean, that could be a James Webb proposal, right?
Yes.
Yeah. So I don't know if there's any existing data, either from HSC or maybe ground-based for those lower redshift ones that you can work on. I mean, to first of all see if the host galaxy flux is consistent with the SCD model, and maybe we can use the results to further constrain the properties of both the AGN and the host galaxy.
Yeah, I agree. I totally agree with the idea, and that's what we are thinking. So for this specific case, the problem is that we actually need a near infrared imaging, and the only imaging we have is from Vista.
That's why I say it's a James Webb proposal.
Yeah, so James Webb or Hubble will work. Yes. Yeah, I agree with that.
What about like other objects in your sample? Are there anything we can do even with like ground-based data to do some image fitting? What do you think?
I think for that we will need at least HST imaging, and that's quite limited. I mean, we have HST data in a small region of our field, but for a wide field, our distribution phase degree square, and I don't think we have HST imaging across the whole field. We only have like we only have such imaging in like Chandra field south or in Candle's field. So
I guess what you mean is like ground-based imaging are just not good enough.
For ground, I think it can be done like for HSC. I know some works decomposing the AGN component and the gas component. I know such kind of works.
Yeah.
And but I haven't really seriously thought about such possibilities. But I think it's a good idea.
Let me protect our time for coffee and suggest that you guys.
Okay.
Sure. Yeah. That's not good. Thank you.
I knew Roberto was gonna have a question.
Yeah. So I mean, very exciting work. So I was wondering though right. So you show one of the issues is that you might be very severely underestimating the volumetric luminosity.
Yes.
But that would also increase enormously your Eddington ratios, right? So I'm wondering if you have thought about that and what implications that would mean for how much larger the stellar mass estimates would have to be to make these objects not be extremely super Eddington, but also if that also might lead you to underestimate the obscuration in the X-rays from the hardness ratio?
So yeah, so your first question is, so if we increase the bolometric luminosity, then we have lots of high adenine ratio sources. I mean, we don't have other ways to estimate this adenine ratio yet, and I suspect that the luminosity is underestimated, and also the black hole mass is probably also underestimated. If we increase them together, probably the adenine ratio will look fine, but I'm not sure. I mean, at least we can have ways to avoid it going to 100.
Right.
Yeah. So that's my point. Yeah. What's
on the second one, because of the right, you would actually get more X-ray emission from the disk itself.
Yes.
So would that lead you? Would that be enough to lead you to underestimate the obscuration base if you just use the hardness ratio?
So and also so for intermediate mass black hole, it's disk emission in the X-ray is still quite limited. I think unless we go to the standard mass regime.
Okay, so even for
yeah.
10 to the 4, you don't get enough to.
Yes.
Okay.
Yes.
Right. Thanks.
Okay, why don't we thank Fan again? One quick slide.
Hey everyone, I'm Brian Kent. I work here in Charlottesville with Ilsang and Mark, and the talks the past few days have just been fantastic. Obviously, LSST is going to be a very data intensive endeavor, and I'm on the organizing committee for ADAS. This is the Astronomical Data Analysis and Software Systems Conference. Maybe some of you have heard of this. The past 3 years, we've had this conference remotely. But now we get to be back in person. It's going to be in Tucson, Arizona in November. And I just wanted to advertise it for this group because I think a lot of the talks would fit in very well with the conference. It's not just software engineering and highly technical things. There is a lot of that, but there's a lot of fantastic science that is promoted at ADAS and presented. There's a lot of great tutorials and birds of a feather sessions. If you do get a talk or poster accepted, there's a 4-page conference proceedings that you need to submit. We'd love to have AGN LSST group participation. I'm here obviously at this meeting, so if you're interested, please talk to me and I'll post this on Slack if you have any questions, okay? So, coffee. All right, thanks.
That introduce Lorena Hernandez-Garcia talking about object that changes its direction.
Thank you.
Very apropos.
Good morning, I'm Lorena Hernandez-Garcia. I'm a postdoc at the Millennium Institute for Astrophysics and the University of Valparaiso, as well as I am part of the LST broker. And well, today I want to talk about a very peculiar galaxy that has dramatically changed the direction of its relativistic jet. And well, here are the collaborators of the work. But I want to make a point here, and is that I want to show an example on how follow-up observations of an interesting source that we can find are done today. Okay, but before, let's start by a very brief introduction on how do we classify sources when we observe them in different frequencies. So historically, in the optical, we would classify a source as type 1 or type 2, depending on the presence or not of broad emission lines in the optical spectrum. And if we go in the X-rays, we would differentiate between obscured and unobscured sources, depending on the column density that we can measure from the X-ray spectrum. And if we go, and if we go in the radio band, well, I know there are different classifications nowadays, but historically they were divided into radio loud and radio quiet, depending on the comparison between the optical and radio power. And this will be related to the presence or not of a jet. And well, if we put these different classifications into the well-known unified model, if we have a direct view into the broadline region and the black hole, we will see a type 1 and an obscure source. Or if we observe through the dusty torus, we will have an obscured or type 2 source. And if we are observing the source in the plane of the sky, we will see two jets, I mean, two lobes. And if the jet is pointing towards us, we will observe blazar. I guess all of us agree with all of this very brief introduction. But then we know that there are some issues with the unified model. And one of the reasons might be related to the fact that AGN evolved with time. And well, we don't exactly know how long does the active phase last. And it can happen that the accretion at one point can vanish, and then something can happen in a galaxy, such as interaction or merging, that can trigger the nuclear activity. And of course, the problems that we have here are related to the time scales, because while humans live, I don't know, like 100 years at most in general, galaxies evolve for millions of years. So during our lifetime, we cannot follow one galaxy. But there is one kind of galaxy which are perfect laboratories to study recurrent activity in AGN, and these are giant radio-galaxies, which are defined as having linear extended emission larger than 0.7 megaparsecs. So this means that the distance, that the size from lobe to lobe is larger than 0.7 megaparsec. And the interesting thing from this kind of galaxies is that the time that it takes the matter to go from the very nuclear center to the lobes can take as much as 10 to the 8 years, while the AGN phase is shorter. It can take like 10 to the 5 years, more or less. So if we observed in the radio, there are some galaxies, these kind of giant radio galaxies, where we can see different phases of nuclear activity. And these are examples that we can see in the literature. So there are the double radio galaxies that look like this one. I don't know where I'm pointing, right here. So we see all jets in one direction, or in this direction, and then closer to the nucleus, we can see new phase of jet activity. And we have also the X-shaped radio galaxy, which are these ones, that we see the old jets in one direction, and in a different direction, we can see new emission from the jets. And there are different scenarios that allow to explain this kind of morphology. And well, it can happen that we have two different AGNs, it's one with its jet, and then we have like two pairs of jets. There's also this backflow diversion model in which we have the jet emitting in a direction, and there's some material from the jet is interacting with the interstellar medium, and so we have material going in a different direction. The jet can also show precession, and it will happen that the jet reorientates at some point. Okay, so now let me introduce you to the galaxy that I want to talk about. Is this PBC J233.92343. Let's friendly call it PBC. And this galaxy caught our attention in first place because it had different classifications when we were observing in different frequencies. So it was selected from the integral sample, so high energy source. And it was a giant, well, it is a giant radio galaxy. And it was classified as a Cipher 2 in the optical, but it was unobscured in the X-rays. And it had some features of a blazar in the radio. So this means that if we put these classifications into the unified model, we will be observing the source through this way and this way and this way. So there was something weird going on with this galaxy. And the first thing that we thought was that it could be related to variability because the classifications were done with different observations taken different dates. So the first thing we did was to obtain simultaneous observations in the radio, optical, and X-rays, and this was in 2015. So we obtained radio with the BLVA, X-rays with the XMM Newton, and optical with San Pedro Martyr. Well, here you can see the radio images. So this is VLA. So here is where it was classified as a giant radio galaxy. So we see the nuclear region and the lobes. And if we zoom in the very center of the nucleus, we see this with the BLVA. So here we see a nucleus and a jet. And what we can obtain directly from this image is that the angle between the observer and the jet has to be smaller than 40 degrees. Then from the X-ray data, we obtain a column density of the order of 10 to the 20, so unobscured. And in the optical, this spectrum from 2009 was the one used to classify it as a Cipher 2. But in this work, we subtracted the galaxy contribution, and we found a broad emission in H alpha, so we could classify as a 1.9, not bad. And then we obtained new spectra in 2015 and 2016, and we found this very broad and strong broad line. And we also found that when we also observed with Swift, and we found that it was variable in X-rays and the U. With this data that was simultaneous, we did the fitting of the spectral energy distribution, and we needed to use a model of a blazar. And well, I don't want to go into the details of the modeling. The important thing here was that the angle needed to be smaller than 6 degrees, so more compatible with a blazar. And well, if you looked at the BLA image, there seemed to not be connection between the nucleus and the lobes. So we obtained this deep image from the GMRT telescope to see whether there was any connection between the nucleus and the lobes. And in fact, it seems that there's not. So at this point, we had an hypothesis, and it was that, in fact, there was a blazar residing in the nuclear region of a giant radio galaxy. So this would mean that if you imagine my arms as the jets, in the past, the galaxy was emitting something like this in the plane in the sky, and then something happened in the galaxy, and the jets changed the direction, and now it's pointing towards us. So it seems that the galaxy dramatically changed the direction of the jet. But with the data that we had, we couldn't prove this hypothesis. It was only an hypothesis. So we needed to ask for more data. And in 2018 and 2019, we performed a multi-wavelength monitoring of the nucleus. So this is the data that we obtained. We observed with Effelsberg in the radio, with SMARTS simultaneously in the infrared and optical, with Swift in X-rays and UV. And we complemented the work with optical data from CTF and Atlas. And well, we performed a first monitoring in 2018 that lasts for about 4 months with a 3-4 days cadence. And then we did another monitoring of about 3 months in 2019, but in this case was only with SMARTS, but we have a daily cadence and complemented with Atlas. And then we also use data from Fermi. So in the work that we published in 2017, the source was not detected with Fermi, and now there is a 6 sigma detection. And we also complemented this study with data from the BLVA from 2018 and RAX and GLASS. And this is what we obtained. So these are the light curves that we obtained from the monitoring. So this is the one from 2018. So this is radio, infrared, optical, optical with CTF, optical with Atlas, UV, and X-rays. And in the right, we have the monitoring that we did in 2019 with the daily cadence, with SMARTS in the infrared, and optical with Atlas. So the important things that we can see in this plot is that first, the source is variable in all the observed wavelengths. The variations are happening in time scales smaller than a month, and it seems to be a flaring behavior. And then with this data, well, this data were the only one that allowed the SMART data that was simultaneous in infrared and optical was the only one that allowed us to do CCF. So we obtained a time delay of about 1 plus minus 1.5 days. So more or less quasi-simultaneous observations. And with all this data, we perform the spectral energy distribution, and we fitted it with the code jet set. And well, again, I don't want to go into the details of the modeling here, but the important thing is again that the jet was constrained to be 3 degrees, so very compatible with a blazar. So then we also compared the properties, the variability properties in the optical of the source with large samples of AGN and blazars that were taken from the LSST training set. So these are well-known blazars or well-characterized blazars and AGN. And we used the parameters from the random walk model that we already heard about them, to differentiate between blazar and AGN population, and this galaxy, the PBC, lies well within the properties of blazars. Another thing that we did was to compare the time delay that we obtained from the cross correlation with theoretic, well, to whether the infrared was coming from the torus, the accretion disk, or the jet, and the time scales that we obtained for the mass and the accretion rate of this source was compatible with the infrared emission as well as the optical coming from the jet. Well, we used also this beautiful image from RAX, which is kind of new image, and it's even deeper than the one from GMRT that we obtained, to again confirm that there is no connection between the nucleus and the old lobes. So after 8 years of work, we can say, or we can firmly say that there is a blazar residing in this giant radio galaxy. So we started this work in 2015, and we have published this paper in 2023. I mean, this year. So there is something that I want to go back now to the point that I wanted to do here, and it's about how are we going to deal in the very near future with, for example, when LSST comes, with sources that will be peculiar, and we will need to follow them up and study them, and hopefully we will not take like 8 years to study them. I mean, we will need a few years, but we need like to, well, I was thinking in questions to myself, like, how are we going to select the sources, or what resources we will need to use? Also, how are we going to deal with the communicability or the ability to use the available tools, and also to know what are the available public resources that we can use to select and to follow up these sources. And I was taking a look at the LSST science collaboration roadmap, and the questions that are in the follow-up part of the document are very similar to the ones that I was making to myself. Well, I put here a few websites that are already developed, and these are mostly used by people that are doing supernova science. But I think we will need to start on these kind of things for the very near future. And then I want to talk a little bit about what we have learned from the coming of CTF, because now that I'm working in ALERCE, we are dealing with light curves from, I mean, not with light curves, but with alerts from the CTF every day. And we are finding very interesting sources that many times need, well, some of them, when they're AGN, they do not need like rapid triggering, but some of them really do need rapid triggering. And well, we have found many different sources. With Paula, for instance, we are studying a few sources that we have finding here. And this is from the experience. So I guess if with the LSST we will have many more sources, this will become even more difficult to select the sources. I want to show a tool that we have developed in ALERCE, which is the watch list. So this is a service that might be useful for all of us, like now and in the future. And what it does is to do cross-match in real time. And when there are new alerts of a new source, we get an email like this. And so we can see that there is a new alert of a source. So this light curve here is the alert light curve for the PVC, for the source that I was presenting. So it was, and in fact, this is the monitoring that we did in 2018. So it was very useful to have CTF starting when we were starting the monitoring. And for example, look at what happened in the last year. There was a flaring, and it was very interesting that with the watch list, we were able to take observations during the flare, because we got an email saying, okay, there's something happening here, and we could trigger observations. And in fact, in a workshop that I have been like in the last month, I remember I listened to someone saying that we need more observations during flares, because there are not so many, because it's very difficult to take observations in a blazar or something that is flaring just by chance. So this can be a very interesting tool, and I will be happy if you have like tools that can be used or that we could develop. In LSST, we are doing services for the scientific community. So if you have any ideas, I would be very happy to listen. And if you have like websites that you already know or that you are already using to do this kind of follow-up, I will be very happy to listen about them. And then I just want to leave the conclusions here. So for this source, we found for the first time a detection with Fermi, so very compatible with blazar nature. We found within the monitoring that we did that variations are observed at all observed wavelengths, and this variability seems to have a flaring behavior. We found also that the optical and near-infrared data show variations simultaneously. With the spectral energy distribution, with the fitting, we obtained that the jet has to be, that the angle of the jet and between the jet and the observer has to be about 3 degrees. And the optical variability properties of the source are very compatible with the blazar population. And again, we didn't find connection between the nucleus and the lobes. So now we can confirm that there is blazar inside this giant radio galaxy, and probably there was a very dramatical change on the direction of the jet of this source. So this is all. Thank you very much.
Question. Yeah. So if you instead assume that the jet hadn't changed direction and that it was still the same, 3 degrees to the line of sight or whatever, how big would that make the radio?
Oh, that would be like the largest radio galaxy. It would be like 13, 14 megaparsecs, something
like
that.
Okay, yeah. That's pretty convincing then.
Yeah, it would be like the largest radio galaxy in the universe.
One could imagine, I suppose, that a tidal disruption event wouldn't have the same angular momentum as a steady disk that's driving jets. So are there symptoms here that this might have been a TDE with its own arbitrary angular momentum vector, which happens if it pointed at us when the material went in?
I don't think it could be a tidal disruption. You mean a tidal disruption event to change the direction of the jet? Because if it would be a tidal disruption event, we will see like one or something which is more like, I mean, we wouldn't see this flaring behavior.
Well, I'm just thinking that the paradox here obviously is the change in the angular momentum of the material.
Yeah.
And so one way of achieving that is to have a particular event, this event with a flare, having a rather different origin to this steady
I guess that the change already happened like long time ago, because if it was something recent, we will still see some connection between the nucleus and the lobes. So I guess this is something very old. We also search for features of a merger, for example, because probably, yeah, the problem is changing the angular momentum.
No, so, well, maybe we're talking across purposes, but I was thinking the current event where you're seeing the blazar now, that was the recent change.
Yeah, but it's not. But I guess the fact that now there is a blazar, it's also old. Now we see features of a blazar which is normal of a blazar, and if you see,
okay, it's fine.
If you see this light curve, you see flaring events. There are flaring events here, and I think there are also some around here. So it's not only one event. It's like I think it's a normal light curve for a blazar.
That's fine. I missed that. Thank you.
Well, just to expand on what Mark said, we have found cases. There was a famous case with Swift J1644, where a TDE that led to the launching of a powerful jet, and that activity has continued for many years after. This happened many years ago, and the thing is still active. And I don't know if it's still flaring, but it certainly did have intermittent jet-like flares. But that case, that particular one, the jet was not pointed right at us. But if you had a system like that one, where just by chance the jet was pointed right at us, it might be able to give this type of laser activity. So
Yeah,
I don't think
yeah,
there may be
understand.
no compelling evidence for it, but it's an interesting thing to think about.
But for example, in that case, did you have like jets in a different direction before? Or
No, no,
because here
no,
we do see
that was
only
a, right, that was a pure tidal disruption. So I guess in this case, you would have to have such an event occurring in a system that was previously an AGN.
Yeah.
I'm not saying that's an analogy directly to this one,
Yes,
but the basic idea could translate.
Yeah.
While you have this slide up, can I ask, if you have an object on an alerts I watch list, do you get notified every time there's an observation, or just every time there's a significant change?
so
in its
right
brightness?
now we get notified every time there is a new alert. In alerts we are thinking in adding filters and this kind of stuff because that will be like very useful. But this will be like the person. But if the scientific community wants it, I think it would be a very good idea if you can like send us an email so that we can tell that to the engineering group, because the engineering group in alerts is doing like many things. And I have been trying to do this like for the last year. But in the future, I hope we will have that kind of filter. But for now, it's only so. For example, I have different watch. So in a watch list, what you do is like you have a list of sources with the right ascension and declination, and it does a cross match. So anytime that there is a new alert, you get notifications. So if you have like a very long list of sources, it won't be very useful right now. It will be useful, like for example, I have one watch list with it's called interesting sources, and there I put like really interesting sources, and anytime that there is an alert, I go and take a look at them. But hopefully in the future we will have that, and that will be very much useful.
There is one comment and question online. The one comment is the new alert means a 5 sigma change from average.
Sure.
And the one question is, how do you determine the time lag?
We use 3 different methods. I think it was like I don't remember the name, like the CCF, ICCF, and CCF. And we did in all the 3 methods we had more or less the same delay, and then we did like mean or something like that.
So my questions, hi, can you hear me?
Yeah.
So it's not about the method, but about the fact that it's determined, like the lag is determined by up to second digit after the decimal. Do you have time sampling of that order to determine the time lag so precisely?
We have daily observations.
Still, like if you have daily observations, you can not you can only determine the you can determine the time lag so precisely unless you have like sampled on minutes time scale.
Saying you're reporting 1.07 plus or minus 1.45, right? Like, do you have significant digits?
You have an even sampling, so you can recover time. If you had recurrent sampling with the same cadence every time, then it's impossible. With uneven sampling, you can. That's the magic of optical observations.
Yeah.
Other questions from the room? Lorena, yeah. Next talk by Samantha Casadei. Talking about she changed her title, so generically AGN and LSST era.
Hi everybody, my name is Samantha and I work at INOF at the Observatory in Turin, Italy. And my supervisor is Claudia Raiteri, but I also work with Maria Carnerero and Alessandro Capetti. Today I wanted to talk about the work that I've done in this few months that I'm a PhD student, and then I wanted to show you the project that I'm doing right now, and hopefully this will be interesting for when we will have the LSST data. The work that I've done is regarding the radio-galaxy environment, and I did this work with the optical photometric data. So basically, I wanted to understand whether radio-galaxies inhabit like galaxy-rich large-scale environments, and whether there are some differences between like the different classification radio-galaxies like classified differently. For example, if there are some differences between FR1s and FR2s, or between HEGs and LEGs. So here I just put this scientific background because some works in the past have already done about this. So basically what we know is that short radio galaxies like preferentially inhabit galaxy-rich large-scale environments. And so that makes radio galaxies ideal laboratories to investigate the formation and the evolution of cosmological structure. So also some previous works have done by Francesco Massaro. He just studied the radio galaxies at, in the local universe, so at redshift lower than 0.15. And he showed that independently of the classification, the radio galaxies have tend to have same richnesses. But his results were obtained like with less statistical significance, for example, for the optical classification of radio galaxies. So what I wanted to do is just have a larger sample and just show, I mean, have a more statistical significant result. So I just studied the 3C sample of radio galaxies. I took the 3C catalog because we already have some information regarding the classification of radio galaxies. So we already knew whether the radio galaxies were like FR1s or FR2s, and whether, and the optical classification, so whether they were low excitation radio galaxies or high excitation radio galaxies. I just splitted the redshift range because, I mean, to have like a sample of FR1s, I needed to be at lower redshift, but I just used two slightly different methods to do that. So this is why I splitted the two samples. And to do this, I used the PanSTARRS data. I think everybody knows what PanSTARRS is, but okay, it's a photometric survey done in 5 filters, and it reaches the apparent magnitude limit of 23.3 in the G band. And I just extracted all the data in an area around my radio galaxy, and I chose like to extract the data in a region of 500 kiloparsec radius. So basically, I wanted to know if my radio galaxies were in a cluster or group. So I wanted to know how many galaxies we have in this region with respect to the background. So I chose like 4 background regions of 5 megaparsec distance from the source, and I just took a background like a medium of this background regions. And the method that I use is the red sequence. That is because we know that at low redshift, if we have a cluster or group of galaxies, the galaxies inside the clustering groups tend to populate a particular region of the color magnitude diagram, which is called the red sequence. So this is a strip that it was observed in studies of clusters up to redshift 2. And basically, these are the early type galaxies populating the clusters and groups, and that we can see in the color magnitude diagrams. Okay, so with the PanSTARRS data that I extracted from the catalog, I just did this color magnitude diagrams of the region of 500 kiloparsec near my radio galaxy, and as we can see, we have like a very well-populated sequence in the diagram with respect to the background. I just used the, as the red sequence, I forgot to tell you about that. I just used the OMIL red sequences, which were like already calibrated in studies of clusters at low redshift. So here we can see that we have a clearly more populated strip. And I also just also highlighted some of the companions that I found with like analyzing the SDSS data. So basically, I searched with the SDSS data if there were some companions near my radio galaxy that were like at the same redshift, and I just highlighted them in the diagram. And once I established the richnesses of my radio galaxies, I just constructed these histograms here, where we have the number of red sequence galaxies and the number of galaxies with the same richness. And I wanted to compare, like I said, like the different classes of radio galaxies. So here we have basically low excitation galaxies and high excitation galaxies. And to compare the two histograms, well, I mean, I guess we can see that already, that the histograms are not statistically different, but I just did also Kolmogorov-Smirnov on the two histograms. That basically is the probability that the two histograms are or not statistically different. And well, so it results that they are not different. Let's see. Okay. For instead the comparison of the FR1s and the FR2s, we are at lower redshift, like I said. So we have a lot of contaminants here, a lot more contamination in our color magnitude diagrams. So we have like more stars in the diagrams. So, well, this means that we have a lower signal to noise ratio. To reduce errors, I just used another method, like I was previously said, and this is done like selecting all the extended, just the extended sources in the diagram. And I did this with a comparison of the magnitude of the PSF and the Cron estimation. So, well, it is, I think, intuitive. If you have a galaxy, the estimation of the magnitude with a PSF, I mean, is not really accurate because you're losing like many of the magnitude coming from the large scale region of the galaxy. So if you want to have a more accurate estimation of the magnitude, you gotta use the Cron estimation. So comparing the two, we can see that the galaxies are populating a well region in the diagram. And so just selecting them, I can reduce basically, well, I can reduce all the contamination in my color magnitude diagram. And what we can see is that selecting just the extended sources here, we have just a well-defined strip, like we can say this well-defined strip. And so the errors associated to my measurement are decreased. And so I did the same thing with the FR1s and FR2, so the two histograms and the Kolmogorov-Smirnov. That so it's also here we can say that the distributions are not statistically different from each other. So the conclusion is that, okay, radio galaxies inhabit different environments. So we can see that they're spanning over a wide range of richnesses, but they're generally not found in isolated fields. And the various classes, so the morphological classes of FR1s and FR2s and the optical classes Hex and Legs are not statistically different. So I guess I can say that there is no connection between the nuclear activity and the large scale number of galaxies. So what I'm working on right now, well, this can be a valuable tool, I guess, to study the environment of radio galaxies, but also blazars. So we can do this with LSST data for blazars. And what I'm working on right now is trying to establish a good way to do the blazar census. So this is my new project that I'm working on. There has been a paper done from my supervisor, Claudia Alfieri, which is based on the variability of blazars in the deep drilling field. And but in this paper, they also did this quite like rough estimation of how many blazars we will expect to have in the sky covered by LSST. So here we have the distribution of blazars of catalogs of blazars that we already know, and from the fact that we know that Rubin LSST will cover 20,000 square degrees, we can just do a rough estimation of how many blazars we will expect to have. And this is like a lower limit. We will expect to have like more than 50,000 of objects, but it's a lower limit. Just just assuming that this parameter here, which is basically the fraction of regular objects that we have, is 4%. But this parameter is really depending on the luminosity and redshift range. So, I mean, I repeat that this is a lower limit that we expect. So how can we do the selection of blazars in the sky? So we have many criteria, many selection criteria. One of them is from the radio spectrum. This is because blazars have this particular spectrum, which is basically two bands. One is synchrotron and one is inverse Compton, and they have a flat radio spectrum. So the flat radio spectrum is usually what we expect to have in a blazar, and it is really the catalogs that we already saw are just were done just analyzing the radio spectrum. But there are also some other selection criteria. For example, the variability is a strong tool. Here I just put the example of this blazar that have this extreme variability. So like it varies from 6 magnitudes. But what we expect to have is not really, well, it's a variability, but not so high. But I just wanted to show you that we can have like also strong variabilities that can be in different time scales and also in very short time scales, so also less than an hour. And this can be studied very well in the deep drilling fields of LSST, where also an estimation were done, and we expect to have 150 blazars in these 6 deep drilling fields. So other criteria are, for example, the colors in optical, but not also in multi-frequency. And here I show you what they were able to detect with the WISE filters. So here we have 2 plots where we can see that we have a clear stripe where the BLF objects are placed, and they're well distinct from the quasar type of objects. So the color diagrams could be also a valuable tool to see if there are any patterns where the blazars tend to inhabit the different diagrams. And also the polarization is a very valuable tool, which is because blazars are very much polarized. In optical, they have like a 10% of polarization, that it goes also up to 50%, but not also in optical. For example, here we have the radio data, which is not really well sampled, but we can see polarization also in radio and also in X-rays. So this is also could be also a valuable tool to select blazars. So what I'm working on right now is trying to understand how to put together all this criteria and to make like the most clear blazar census. I just started with the VLASS data. I just selected the point sources, the radio point sources, and I matched this catalog with the PAN-STARRS data to search for optical counterparts. So now I'm just constructing the color diagrams to see if there are any patterns, for example, like we saw in the WISE filters. And then I will study also the other selection criteria. So the polarization, the radio spectrum, I will try to construct a set and also check the variability so that I can construct the most clear catalog of blazar. And hopefully this will be used also in the LSST part of the sky when we will have the LSST data. So, well, here I just put it another project that we were thinking about, but that I didn't really started yet. So the search for high redshift radio galaxies, basically, because I mean, I just started to my PhD analyzing radio galaxies, and like we saw, like radio galaxies could be like a probe of rich environments. So they could be a probe for proto-clusters. So this makes them very interesting. So the selection of high redshift radio galaxy could be very interesting and study these proto-clusters and the history of the large scale structure and their star formation rates. And we were thinking to do this using the photometric dropout technique. So basically we would like to have like a to have a pipeline that does the selection with a dropout technique. So yeah, that's okay. That's it. Thank you.
Question.
Yeah, so very nice talk. So for the blazar selection, we now have 2 epochs of, well, 2.5 epochs of VLAS. So you could have you thought about trying to look for variable sources between the 2 epochs as well as?
Yeah, that could be yeah, that could be checked, of course.
Yeah, we already talked offline about selecting blazars from the X-rays and the radio, but it just occurred to me that there is fairly extensive optical photometric monitoring already that's been done in the deep drilling fields from DeChico et al. and others. And have you had a chance to look at any of those light curves to see if there's any distinctive flaring optical variability among those?
Yeah, sorry, not yet, because I just started my the project on blazar, so I didn't have the chance to do that yet.
Okay. Yeah, I think though the optical light curves are available, and there probably are other monitoring, optical monitoring projects on those fields which you could access.
Other questions in the room or online? So more for discussion afterwards, but I spend a lot of time now talking with the IceCube people about astrophysical neutrinos, and I'll just say that they don't know enough about AGNs, and I don't know enough about neutrinos, so there's opportunities to have cross communication. So.
Okay.
Yeah. Okay.
Hey, Gordon, just to say, yeah, I mean, so Paula with her classifier model and some features, basically the optical variability properties plus some radio to optical ratio is actually very good at finding blazars in FSRQs, flat spectrum radio sources, and actually splitting them up.
Thanks, Brandt.
Okay, other than Fran's advertisement, other questions? All right, if not, let's thank Samantha again. All right, last but not least is our host.
I'd like to move my slide.
Do you need someone to advance the slides for you? Sorry? You need one of us to advance the slides for you.
I can do it.
You've been doing it the whole time. I don't know if you can find.
Last time is going to be talking about changing look object Markarian in 1018, I believe. Yep.
Okay. Thank you, everyone. Last talk. So it's a simple. I'm going to talk about basically what's happening in the Markarian 1018. Just to give you some idea, this is the single object monitored over 40 years of time with a spectrum, photometry, etc. So I'm going to tell you the story a bit. And before I get to that point, I would like to point out that these galaxies, as you see, this not a the very nice looking isolated system. It's a so-called post-merger system. Two galaxies actually merges at a long time. They have a very complicated structure like the tidal features, and inside still there's a bright nuclei, which this is not a quasar, it's an AGN, but these AGN varies. So I mean, I can imagine in the LSST operating because of the exquisite, surface brightness depths. I mean, we probably will have something, the system like this. Interesting about this system is if we believe that every galaxy have the supermass black hole inside their potential center, and it's very natural. For example, for like this system, if there are two galaxies merge or three, I don't know, but eventually if the black hole survive, and potentially there could be not just the one black hole, could be a two. So it's really an interesting object. In a broader context, actually, it looks like a single nuclei, but if you're actually looking at the system like this, we often find there are two objects. For example, this one, the same, post-merger system background HST images, and obviously this optical nuclei is not exactly on the host galaxy potential center, but it's off. So we thought that, okay, it's offset nuclei, but actually if you look at the radio images, you see it in the middle panel showing that the white contours and the very blue contours are showing you respectively VLA and the VLBI imaging, which is not from this optical nuclei. So if we believe this emission is AGN, we could say that, okay, there are two things. One is the optically bright AGN versus the other, the radio bright AGN. And there are other examples like this. It's the program of a follow-up observation of the other sources. Overall, these post-merger system, again, tidal tails looks like clear as a merger remnant. And these are black contours are the VLOS contours, the 3 gigahertz images. Yeah, there looks like a large scale jet emission here. But if you just putting in the VLBA, and this images has a two blobs. Obviously, it's a one band imaging. It's still possible there could be the jet. But if you believe that the direction of the large scale jet emission here, it looks like these are the two the separated source apply 34%. And the other example, like the ground-based NEO imaging actually shows the multiple nuclei. If these are the most ground-based imaging without the good resolution. First of all, looks like it's a very nice looking optical, the nucleus emission is very smooth, but if actually using it high resolution ground-based AO imaging, you got the multiple nuclei. So the supermassive black holes in galaxies in general, it's not necessarily the one single black hole, could be the more complicated. So what I'm going to talk about is, okay, so some of these galaxies could be the changing look AGN. Obviously, LSST will just monitoring the light curve over the many years, like the 10 years, but some could be the changing AGN. And as Chris already alluded in his talk, could be the very extreme case of the variability in the damped random walk process, very long time scale variation, possible. But could be also possible scenarios, okay, what if that the physics itself is different? It's not just the extreme outlier of the variability, but the external effect actually caused the changing of behavior. So in that sense, I guess the detailed investigation of the single object might be more useful than just study the large statistical sample with the sparse information. So I'm going to talk about how we actually collect that information and do some exercise to test the scenario. So first of all, these Mercurian 1018 work actually reported by this group, CARS group. They're actually monitoring the closed AGN using the MUSE program. So they have several candidates, and one of the earlier paper from their group is actually reporting the Mercurian 1018. These are the first paper and the second paper. So this is an example. The optical morphology and the the left-hand side is a slow distance sky survey around the 2000 epoch and year 2000, and the right-hand side is the MUSE images obtained by 2015. So obviously, this nuclei was very bright in the SDSS. Now it's a little fainter. And if you look at a spectrum, these are the spectrum obtained around. Okay, 1986, 1981, now it's a 2000 black here, and the mu spectrum, which is blue, is at 2015. Clearly, spectral shape itself is changing. And these are the photometry starting from around 2000, and it stayed more or less constant. Then as time goes on, it gets dimmer and dimmer and dimmer. And the right-hand side is the X-ray spectrum obtained by Chandra and the new star, and the combined spectrum around either 2010 black and 2016 blue and green. So based on these, the exercise, they argue that if it's a TDE event, I mean, this constant, the brightness, for over larger than 10 years is unlikely if it's a TDE event. So they actually think that it's not likely the TDE event. Also, if you look at the X-ray spectrum, the both spectrum requires no additional neutral hydrogen column density, but the galactic, except for the neutral hydrogen in the galaxy, they argue that the line of sight obscuration scenario is also less likely. And this is the Lyman alpha spectrum obtained around 1996 and 2016. The red is the 2016 and the blue is the 1996. The number 2 here is the new absorption feature obtained in 2016. So the new Lyman alpha absorption around 2016 also suggests that there could be the gas cloud moving, in front of the system, emission system, or the black hole itself is actually moving. So it could be just the line of sight obscuration happen at the certain, the period of time. And the right-hand side is the SED modeled by the geometrically thin relativistic accretion disk. Fits the data well, but they actually need to change the luminosity of the accretion rate to fit to actually match the data point. So overall, this exercise actually telling us that, okay, this system somehow changing its luminosity by just decreasing its accretion rate or the intern ratio or whatever. The luminosity is actually dropped. So then later they reported another observation. The previous photometry stops around this, but afterwards they got more photometry at around 2017. They see that the system gets brighter and stay for a while. And this X-ray spectrum on the right-hand side, the blue and the greens are the 2 previously obtained spectrum, but the red spectrum is actually newly obtained around 2017, when this system starts to become brightened. So X-ray spectrum itself has a little bit higher flux density than the previous 2016 data point. So the overall story based on the paper is that, okay, until 2017, the luminosity declines and the broad emission line disappears. And the TDs and the other obscuration scenario is ruled out. And the remaining hypothesis sort of is, okay, so somehow accretion rate has to be changed, either due to the external, the effect or the kinematics of the accretion disk itself. So then we start to play, okay, what if we collect every available, the data historically obtained, and we try to compile the spectrum from this one is actually not used there for analysis, but to just give you some idea, it was already obtained by 1974. But it's obviously resolution is not something we can actually look at. So we actually start to look at a spectrum obtained around 1979 and the 2015. These are the H beta O3 emission line region, and these are H alpha. So you will see that there's no broad emission line. We still see the broad emission line stronger, 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 and the decrease it again. So basically, change in loop behavior happening from so-called type 1.5 Seifert to 1, then going back to the 1.5 type over a period of the 40 years. So, why? So we try to decompose the spectrum into the multiple component. This is pretty the standard exercise of looking at focusing on the H alpha region and decompose into the two broader component, and the blue and the red, and the one H alpha narrow emission line, H alpha, and the two N2 and the S2 lines. And we do the same exercise for every spectrum we obtained from 1997 to 2015. Then we focus on the broad emission line, because that is actually tied to the accretion disk itself, which you believe that the physics. I mean, the narrow emission line is much more larger scale, but if a black hole somehow moving, it's likely that that carries the broader emission line. So we actually try to monitoring the broader emission line and how the kinematics could be interpreted in terms of the recoiling supermass black hole scenario. So just we come up with this like a cartoon scenario. Okay, what if this is the line of sight we're looking at, and the system itself actually moving into this direction. 1984 moves around this and move back. So this is the scenario like, okay, if it's a black hole is kicked out of the galactic potential well, and after a long time, it actually starts to getting into the center of the galactic potential well, then it shows the damped oscillation. So it's not really, doesn't mean that this black hole itself is actually gravitationally bound to the host galaxy potential, but it's because of just kicked out and going back to the potential well, it actually showing the damped the oscillation. So we try to model this orbit using the centric anomaly E and the eccentricity and the period. This is pretty much the orbit that we studied for the binary and this, the star, the motion. Then we just write it out, okay, this is a line of sight velocity that's composed of X and Y components, and the orbit itself is actually slightly tilted as a function of the moving as a function of time. Then, okay, this is just the fitting. And these are the red and the blue points are the velocity measured for the red component and the blue component of the broad emission line. These black points are actually the average of these two. Okay, this scenario is kind of fitting the data, but unfortunately, yeah, this is just about one cycle. So it could be coincidence, or it could be the real. We are not sure yet, but this is actually makes me think, okay, what if this scenario is real? I mean, is it really possible? I mean, the simulation here on the left-hand side is often, shows the motions of the recoil supermass black hole after two galaxies emerge. It actually kicked out of the galaxy, then it falls back to the galaxy potential well, then it shows like a damped oscillator motion like this. So this damped oscillation of recoiling supermass black hole, it's within a galactic potential well, should have the very high, the eccentricity of it itself, it should be very high. And the thing is, if the black hole is actually past the pericenter, and whether there is the very concentrated star clusters or there is not any matters of it, potentially the disk can be perturbed. So if the disk is perturbed and they need we need a long time scale to actually erase the memory of the perturbation that related with the sound crossing time across the accretion disk scale. So that sound crossing time is about tens of years, like the 70 roughly, and which is significantly bigger than the thermal, larger than the thermal instability time scale. So we are thinking whether that scenario is actually might explain, okay, 40 years of the variation of the Makarian, 1018, which is clearly is larger than the year time scale of the thermal fluctuation. Right, then I'm going to talk about the more recent story. Then after this, we could collect some more photometric data point from the ZTF here. And this shaded line is actually showing in this zoom in panel on the right hand side, 2016 versus 2017 here. Okay, so the disk itself, it's become Brightman, but it's not actually systematically increasing. It's more or less like the state, stay in the, I would say, quasi-static. Okay, there could be some fluctuation from the ZTF data points, but it's not dramatically increased. And the other story is from the radio side as well. And a recent paper published by the Greg Walsh and the grad student at the University of West Virginia do the VLBA follow-up monitoring. The 2 epoch observation around 2014 between 2016 and 2020, 2021. These are the VLBA observation, multi-frequency, the four observing frequency from around 2 gigahertz up to almost 10 gigahertz. These are the early epoch, around 2015, and spectral shape is clearly steeper. And later epoch, 2021, spectral shape is flatter. That is before actually the system becomes dim, and this is actually the later epoch, the accretion disk becomes fainter. And the right hand side is showing you the core offset, which means anything we see radio emission actually from the region where optical depth is around 1. But that region is different if you're choosing a different frequency. So usually if you pick that high frequency, you can prove the more inner region. So we actually, this person in the paper measured the centroid of the radio emission at a different frequency and try to calibrate that with the reference position and the fit this relative offset here. Again, early epoch 2015 and later epoch 2021. The point is these two curves is actually consistent with the predicted model. So there is no big the difference between these two epochs. But the interesting observation is they reported the proper motion between these two. So after this, the epoch around 2016, then accretion disk becomes brighter. Then later epoch, accretion disk becomes fainter. But between these two epochs, they reported like the 10% of the speed of light in a proper motion. So which means clearly this proper motion is likely to be a jet. And also in the private communication, I also know that the other VLBA monitoring reported some secondary emission around 2016. So something happens in between. So either it's really due to the kinematic motion itself, we are not sure, but around this 2016 epoch is where the system is actually far away from the pericenter. So if this actually passed through the pericenter, got disturbed, and it has went back far away from the pericenter, it has some time to actually collect the material surrounding it, probably try to play something else, either just eating the material and creating more energies. So this type of the observation clearly requires the longest time scale monitoring. So this is summary for the future. I mean, so we are thinking about proposing the higher resolution radio imaging, which is a global millimeter VLBI. So still the VLBI shows that the emission itself, the single point source without resolving any of the structure, but the things that showing that structure itself showing the proper motion, still possible whether the secondary emission is resolved if we use a higher angular resolution instrument. So this we are trying to do, and also we are trying to do some spectral follow-up observation because the spectrum we obtained around 2017, the 15 or 16. So we need the later spectrum, the spectrum obtained at a later time, and more importantly. So LSST will give us the tons of images with the very the good surface bright sensitivity. So we would like to have the candidate like the Makarian 1018. So we will see more of the post-merger galaxy system, and also we will see some light curve variation from that. Clearly, some of them shows just a long time scale, which is not well described by the class canonical dense random walk process. Then we will be able to find some interesting candidates to actually figure out and monitoring, with the other follow-up instrument to see what's really happening for those interesting rare objects, which potentially relate with the changing look. This is all I wanted to say. Thank you.
Questions?
So on the spectra you showed,
Yeah.
when it was going from type 1.5 to 1, then back to 1.5, is it my idea or the broad H alpha doesn't seem to be getting broader?
With the thing is, the broader H alpha line, there's the absorption. It's persistent. It's everywhere. So we haven't really tried to measure the shape very accurately. The broad H alpha region is actually changing. I would say by looking at this, I mean, looks like their change is not very dramatic, but actually, if you measure it, it changes. You know, it's not very prominent as the other H alpha. You know, the H beta emission line. But clear, I can say that H alpha is also changing, but the only thing that I didn't mention is because it's not as prominent as H beta line.
Right, but I think if I understood the model you're proposing correctly, then a prediction is that H alpha should become significantly wider when you're lowering the state, right? That when you're lowering the emission because you're kind of running out of material, so your BLR has to be moving inward.
Lowering means the luminosity.
Right, you're lowering the
fainter, then H alpha should be.
Right, because your BLR now has to be significantly closer to the black hole.
Yeah. Okay. If it's a lower, I mean that this could be one of these on the spectrum, and this.
Right, it would have to be a lot in a way that should be predictable just from the lower accretion rate. Right. Right. Just
okay.
the width, not the flux. I'm interested in. It's just
I mean the line width you care about. Yeah. Yeah, you might be. I need to go back to just to see the numbers, but from the picture itself, I don't think, I can't really give you some numbers yet. Sorry.
Can you go back to the slide with the ellipses and the physical model? Yeah. Apologies if I missed this. Can you say what is the physical scale you're talking about? What are the units on the axes?
Oh, this is the normalized by the where is it? The A here.
Okay, so what is that?
It's very, very small. Okay. It's like the percent of the parsec. So this could be the worrisome because if you're assuming the inclination effect, right? That could be one explanation. But if it's a real, the 0.0014 parsec, for example, this is very small orbit.
Yeah.
So I don't think I'm not sure we can have this orbit, but the only thing that I can imagine is it's just assuming some inclination. That could be one explanation. So where is it? If you believe this A value as a disk size, I don't think it's we shouldn't have that small disk. Only thing we can argue is, okay, it should have some inclination angle. So that actually looking at something is coming directly out of, the galaxy or just, into the galaxy itself.
Yeah. So if you wanted to generate more sources like these from like this one, from Rubin data, this source historically, of course, was selected back in the 80s, as you talked about, from Cohen et al. And so on. And it was noted as being remarkable based on spectroscopic data. So is it the case where you just have to pretty much follow up every single change in AGN photometrically identified, or does this source have some distinctive aspect to it that you could home in on to identify such things from?
So at this point, personally, I think it's more important to do some more follow-up on this single source to figure out, convince ourselves, at least to rule out some scenario. Then we can go back to the larger data set, see if we can find something similar. But without knowing, much about this system further, I don't think it's no point of just exploring the light based on just the LSST light curves to actually do some, follow the experiment.
Right. I just thought, given that this is a conference on Rubin data, it'd be interesting to think.
Yeah, but the point is, I'm only thinking Rubin data, the LSST is actually the very big playground, so we can actually always find this kind of similar examples.
Right.
Then we can actually build up some statistical sample that share the similar properties like this.
And that's my question then again is, so does Markarian 1018 stand out as notable among changing look quasars in general? Is there any signature that?
Yeah, I know there are other people actually working on the changing look AGN, and I know some very nice, the photometric light curves, which is, the very significant near variation. So again, this is just the one scenario, but what is the origin of the changing look behavior? There could be a multiple origins, right? So I don't think this is just that we have a single origin for that.
Okay.
So I guess that's why we need to test the multiple. If there is a multiple scenario for the changing look behavior, I need to test those scenario, actually rule out, at least to rule out some. Then we can actually say this is reasonably well explained by the scenario A.
Right.
There could be other case like, that could be explained by some other scenario like TDs.
Right. And so to get the final answer on this, or you have the smoking gun to know if the model shown here on the screen is true or not, you'll do the you mentioned at the end, the millimeter or whatever BLBA to check the morphology.
Spectrum and the radio imaging.
Yeah, right.
That's sort of the near term we are actually pursuing.
Yeah, and so given that the period is 40 years, I mean, how long of a radio very high resolution monitoring would be required before you'd be confident that indeed it is moving in the way predicted? Like, do you have to wait 20 years for it to turn around out of apogee or whatever? Or
I don't, if it's a really a very small scale, that we won't be expect to see any significant proper motion in the radio.
Yeah, okay.
But the spectrum already collected for the 40 years. And the one thing we can do is keep collecting more spectrum now and few years after.
Right.
Then if we actually have more, the kinematic data points, we may be able to say, yeah, this scenario is wrong when we did something else.
Sure.
Then the radio imaging is just for telling us, okay, the galaxies are still point source.
Right.
So the thing is it really, really point source, or is it there's actually something in actually unresolved the radio emission? That will give us another clue.
Okay. So the kinematic data, I mean, I guess you could falsify the model rather quickly, but to actually convince yourself the model is true, I mean, typically people want 5 or 6 cycles, which means that's be 200 years. So we may not have the opportunity to actually know if it's true or not.
Yeah. But as a human being, so what I mean, thinking like
right. But it's a good long-term goal for humanity.
Yeah, we have very few cases like this.
Okay.
Yeah.
Well, speaking of falsifying, I couldn't quite decide whether you were able to get a length scale so that you could derive a mass that's interior to this orbit. And if you assign that to stars with a mass to light ratio, then you would be predicting a certain luminosity in the stars, and then you could check, is that consistent with the imaging data? If it's not, of course, you can always fall back and say, that it's in fact orbiting the second black hole, and that the mass that's causing this orbit is a black hole, not the stars. Do you have a preference or a thought about that?
One of my friends actually criticized because of that exact, the comment, and they actually use this orbit, try to estimate what is the mass at a pericenter. But that mass is actually very, very large. If you want to hold this, the mass black hole in Makarian 1018, you need a very mass. So that's why I'm saying that this is not the gravitational bounded orbit. If it's a gravitational bounded orbit by the one object, for example, point mass in the pericenter, that mass should be very, very large. So I don't think it's I think it's unlikely, but to actually to find out if there's any significant mass concentration resolution, I don't think we have no good way to actually
if you put together velocities, kilometers per second, you have a time scale, that gives you a physical length. Plus the velocities, then you have the mass. I don't quite understand what you're saying.
Physical length is already sky projected. That's the point. If you just vary that length quite a bit, you can actually have some wiggle room here. So unfortunately, my perspective is actually very important to actually see whether we are sure there's a single point source or not. Then if that's the case, we might just start thinking about another scenario, but that's hard.
Any last questions in the room or online? Online, feel free to
I don't
unmute.
think so.
Nothing online.
Great.
So I guess